So I've been asked to talk about some of the nuts and bolts of nutrient management with corn. So I'm going to show you some things that are really nuts and bolts. They're no big picture things, but they're components of what you might need to think about. Little things that are nice to tuck away. But before I do that, I probably should tell you, my shirt here says Schepers Consultants. My wife got me these shirts. She says, I got to get you out of the house. And I work as an expert witness for insurance companies. So farmers or cooperatives and fertilizer dealers that have really nasty cases, they sometimes call me in to help them figure out what went wrong, why it went wrong, how do we settle this thing out of court. So very interesting. Well, I think it would help if I could go back just a little bit to tell you about where we come from and why we're doing this. Back in 1990, there was a lot of concern about groundwater contamination with nitrate and atrazine. And so President Bush, he set aside a pot full of money. He said, we want you to figure out where we are and how we can do it better. We want to address this thing. And so the last item there is to develop some new BMPs to try to take care of this problem. This was open competition, and there were 5 states identified. Nebraska was one of them, so that means me, I'm part of it. But the other part of it is, it had to be in conjunction with university people to get the word out. So the USDA part was the longer term activities, the universities was the extension and communications part of it. So with our Nebraska project, the conventional activities at the time were just plain furrow irrigation. This is mostly in the Platte Valley. So furrow irrigation, quarter-mile or half-mile rows, various soil textures, this sort of thing. So there was a lot of potential for nitrate leaching. One of the better ideas was we can use laser grading to get that field level, so we could do a better job of irrigation and then put in some recycling activities to bring that water back and reuse it. At the time, there were very few center pivot irrigation systems in the valley. There was none. So when we started putting up a center pivot irrigation system, lots of comments. What the hell are you doing? We don't need that kind of stuff. But what we wanted to do is to be able to spoon feed the crop, put some fertilizer in the water. And so I was the agronomist side of this thing. And we were getting $1 million a year. $1 million a year for 5 years, guaranteed. And the last thing I wanted to do is to make a mistake. This had to be very visible. So anyway, I was concerned about where something could go wrong. I heard somebody talk here about Murphy's Law. If it can go wrong, it will. And we wanted to avoid that. So one of the questions was, if we stress this plant early in the growing season, are we going to run into trouble? We've lost our potential for high yields. And the logic was, it's really hard to put a nitrogen stress on corn plants for a week or 2 at a time. How do you do that? Well, one thought was, nitrogen will affect photosynthesis. And if we can somehow affect photosynthesis of the plant, we might learn something. So our thought was, we're going to screw around and we're going to go to the greenhouse idea, put some sunscreens over the plant. We're going to shut down the light for a week or for 2 weeks, and maybe we'll learn something. So that's what we did. We built some, I'll show you a picture in a minute, sunscreens that cut out about 50% of the light. We put them on for a week or 2 weeks and moved them around the field. So here they are. This is one picture of it. These are 6 foot tall, 4 feet square, with side screens like this. We figured out, or learned shortly, that you had to tie them down really well because the wind blows in Nebraska. One of them was a kite. But anyway, we would move them around, and what we found is that you put them on for a week. When you come back, those plants are going to be 3 inches taller than the ones outside. They're looking for light, they're growing taller. So what we learned? Well, at about the 4 weeks, this is about the B5 to B7 growth stage, seems to be, from this study, about when we started getting this reduction in ear length. And we've heard about ear length this morning already. Our other thought was, well, our soils in Nebraska have a lot of residual N, and some of yours do too. So how can we do this sort of thing with nitrogen? So we went and got some wheat straw, chopped it up into a chopper, spread it out on the soil, and rototilled it in. So we're going to get rid of that residual nitrogen. And so that's what we managed to do. We tilled it in and then planted through it. And what we did is, after 1 week, 2 weeks, 3 weeks, we would come in and add 80 pounds of nitrogen as a liquid, water it in, so that we would essentially figure out which section of time was going to cause the trouble. What we found is that, once again, this B5 to B7 stage is when it determines the number of rows of kernels. Once you've lost that, you've potentially lost some yield potential. So that's one little piece of the puzzle. Okay. Here's an example. You've seen that sort of thing before, different rows of numbers. But you can also see that there's a potential difference in yield potential there. So one little piece of the puzzle. So another question we had is, a lot of farmers in Nebraska use starter fertilizer. And the question was, well, if you've got a soil that's already got residual nitrogen, that's mostly nitrate in it, do you really need starters? And what's the best form of starter? So we had some young corn plants there. And the question was, do we use ammonium or nitrate? Well, if you use ammonium, we know it attaches to the organic matter. It's more efficient within the plant. Bugs are going to convert it over to nitrate anyway. If you've got nitrate, it's soluble, it's going to get away. It can enter the plant in the water stream. And it's going to have to be converted back to ammonium, or the amine form, before it can be used to make proteins. So which way do we go? That's the question. Where do we get these different sources of starter fertilizer? These are some ideas that you might say for experimental purposes that are only nitrate or only ammonium. But the bottom one, look at the bottom one. Tagged ammonium nitrate. That's a tracer. It can be a tracer. So that was the idea, that a lot of the fertilizer we use, it all comes from nitrogen. We heard George talk about the German technology came from about 1909 or 10. The Haber-Bosch procedure to make anhydrous ammonia is still used today. But once we get it over to the ammonium form, then we have the potential to do something with it. The nitrogen in the air, it's mostly has an atomic weight of 14. But there's a wee bit, just a little bit over there, that's heavy nitrogen. N15, it's a tag or a tracer. So they call them isotopes if you hear about that, but don't get afraid because it's not radioactive. It's not going to hurt you. People hear that word and they say, oh my God. Anyway, here we go. It's heavier. It tends to move a little slower in the metabolism. It's heavier to get at, just a little bit slower. So, cost-wise though, that heavy nitrogen is expensive as hell. Probably $2,000 a pound. So we don't use that very often. The other one, about $200 for a kilogram. So a whole lot more, or cheaper. So what we did, we went back to this this idea of early season young corn, and we had to make some ammonium nitrate fertilizer that we tagged either the ammonium, so when it says 15, we tag the ammonium, or we tag the nitrate. And we could follow that when it gets into the plant to see which one was used. So what we found was that up until the V3 growth stage, those plants preferred to use the ammonium form. They preferred ammonium. But once they got up to V5, that plant had developed the nitrate reductase metabolism and procedures within the plant that it could use that nitrate. I talked to an old professor from Illinois, Dick Hageman, and he said, well, those young plants, they just don't have the ability to take up and use that nitrate to start with. They don't have a way to convert it to ammonium, to be used to make proteins. But also what happens, remember, that we've talked about any ammonium you put in the soil, it's going to end up over here as nitrate. The bugs, the microorganisms are going to move it over. How about later in the growing season? Fred Below from Illinois started a project when I was on sabbatical leave back there in '83. So this is a long time ago, and it tells you how damn old I am. But anyway, people are concerned about greenhouse studies with hydroponics and all this sort of thing where they recycle the water. We went into the field and we had a bunch of 55-gallon plastic drums. We dug holes, put in a drainage system to recirculate the water. So they were at ground level, filled them with gravel and sand, and so they had a field hydroponic system. And what he found was that those corn plants, they prefer a mixture of nitrate and ammonia, if possible. And part of the reason is to balance the electrical charges, the nutrient uptake of potassium versus chloride versus phosphate in the soil. So the plant would, if it had a choice, it would tend to use both of them, or either one. So, the other question is, one of our graduate students, Tracy Blackmer, some of you may know, heard the name Fred Blackmer from Illinois. He was a graduate student, and we were talking about part of these nitrogen uptake functions and curves that were developed back in the 1950s by the folks at Iowa State. Are they real? And Tracy told me, he says, a lot of those were done in the greenhouse. And that immediately raised a red flag. And we better be careful of this. And so we set up a study. We went to Pioneer and said, how about giving us some more money to check this out? And so they gave us $20,000. So the idea was, we got 3 hybrids from Pioneer, different wide leaf plant architecture type things, plus 2 more hybrids. And then if you remember B73 Missouri 17, anybody remember that number? You heard it, okay. This is an old-time hybrid from back in the 70s, but about 50% of the land in Nebraska was one time planted to that hybrid. It's a good reference. And so we had 3 replications. We had starter fertilizer. We had, now every week from V3 up to soaking, we would go out every week, take 18 plants, tear them apart into the appropriate components, and get them analyzed for all these different nutrients to verify that these nutrient uptake functions were realistic. What we found is that in most cases the functions in general follow the same path. I'll show you some in a minute. But the timing of uptake was specific, especially late in the growing season for some of these hybrids. They behave differently. I'll show you this kind of graph a couple times, but mostly to illustrate the nutrient uptake functions of the corn plant. The longest growing day of the year is when the plants are fairly small yet. best photosynthesis occurs in mid-July. And that's because of the optimum balance of temperature and light growing degree days or light intensity. So this is one of the first examples. I apologize for the metric unit here. If you multiply those numbers by 16, you'll get pretty close to bushels per acre. But anyway, notice that early in the growing season, there's a lot of similarity. But you get out close to the end, there's apparently some funny stuff going on. And one of the ways to understand that is that out here at the end, we have probably 15 or 20% difference. Something's happening there. And so we normalized it. What this means is that we now are going to handle each one of these hybrids separately, depending on what its final value was. Everything's now going to be on a percent basis. So here we are. This is one of the first ones. What we found is that soaking time is about 60% of the nitrogen is taken up already. Within about the last 4 or 5 years, Tony Vine from Purdue University verified this with some of the new hybrids. Now this is the difference that's happening. Across the bottom, this is calendar day, and this is percent of the total. Remember, it's percent now. But this is now averaged across 6 hybrids. Potassium, that stinker's taken up early. Potassium's involved in essentially blowing up, keeping the leaves upright. Plant trigger. So that's what potassium does. It's taken up early. It's got to be there early. Phosphorus, it's taken up later. Here's dry matter. You've got to put the nutrients in there first before you're going to get the dry matter out. Common sense. So what about this one? Nitrogen. Somebody talked about the corn plant going on vacation, going on break. I told you that Pioneer paid for this. And so we went back to Pioneer. And some of you may recognize the name Dale Flowerday. Anybody? Dale Flowerday used to teach it at the university. And then he was hired off to be the agronomist for Pioneer. Well, Dale, he would probably be in jail today for inappropriate comments had he lived in this era of time. But anyway, when we showed him this, he looked at that a minute and he says, what was happening then? I said, well, this is about soaking time. And he said, well, I'm not interested in eating when I'm having sex either. That was his comment. But anyway, this was happening with all hybrids. We repeated this study a second year, and it happened again. So this is something that's very real. We'll show you a little bit more about it in a minute. But this is just the growth pattern, and what I wanted to show you here is that this nitrogen uptake pattern up until soaking time can be very intense. The plant's going to have to want to take up 5 to 7, maybe even more than that with some of the new hybrids. But the nitrogen uptake curve is very rapid, and there's this period of time in here where there's an opportunity then for spoon feeding or fertigation, if you have fertigation, or slow release nitrogen might fit in some cases. Anyway, to make sure that you fit that need. So here we are. Remember, this thing is normalized now. So this is relative nitrogen uptake and relative dry matter. So you get to the end of season over here, everything's 100%. Early in the growing season, things are very similar. This is the period where the plant is pollinating, where it's going through that vacation period. But look at all this various stuff going on out here at the end. And you might say, well, hell, you guys, look at this mess out here. It looks like you lost nitrogen. We knew that was going to happen. We suspected it might be different for certain hybrids. But what we had known is that some of our tracer N15 studies had showed us that near the end of the growing season, some corn hybrids pass more gas than others. And that gas that they're passing is ammonium. As the plants approach senescence, they're not able to capture or to recycle some of that nitrogen in the system, and it comes off as a gas. So we've measured it coming off as ammonium. Even with check plots, with no nitrogen, we were losing up to 30 pounds per acre. With high nitrogen plots, it would be 60 pounds per acre coming off some of those hybrids as a gas. Now that doesn't mean that it's gone forever. It could be taken up by other plants in the field, and it's even specific for the time of day when it comes off. So it comes off, tends to come off in late afternoon when the temperatures are high, but it might be absorbed again in the evening. So anyway.
Gassed out from where?
Huh?
Gassed out from where? The roots?
No, it comes out of the leaves.
How could you get it back? Wouldn't you just blow it up and up?
No, see, leaves can also absorb nitrogen out of the air. If you look at corn plants downstream, down air from a feedlot or chicken house, those plants are greener. They're picking up nitrogen out of the air. They can do it. So here's another analysis that I found in one of our old slides, but at the 10-leaf stage, that's about the point where you can use a high clearance sprayer to get in there and provide some nitrogen. Here we've already talked about 60%. The important thing is that 40% is still yet to go. So how late can you put that 40% on? I think we're going to get to that in a minute. But at soaking time, and you consider how much total nutrient is taken up by the plant at harvest. So at soaking time, let's take sulfur. About 50% of it is already in the plant for sulfur. Another big one, nearly 90% is in the plant at soaking. It's in the leaves. That's what's keeping the plant upright. Phosphorus, oh, it's only 40. And nitrogen, that's about 60. So now we're going to look at it to see what happens at harvest time. So at harvest time now, this is across those 6 hybrids. Let's look at the harvest index. This is dry matter. That's about 55%. Very common. If you have drought conditions, it will go down to 53 or 4. If you have a really good growing season, late in the season, not too much heat, plenty of moisture, you get up to 61 or 2. About the total amount of nitrogen taken up relative to that's in the ground. That value is 70%. That's a good sound number. For those of you growing soybeans, it's the same number. 70% of the nitrogen uptake is going to be hauled off from the beans or the grain of corn. How about phosphorus? 0.45 pounds P2O5 per bushel. So let's stop here a minute. Any of you growing 200 bushel of corn or selling fertilizer to people producing 200 pounds, 200 bushel, are they putting on 90 pounds of P2O5 per acre? Probably not. I talked to Ray Ward, and he says that the soil P levels in general are coming down and down. And partly because people are mining the soil. It used to be when all they had was rock phosphate, and it was cheap, people were building up their soil, and now they're mining it down. Last one, sulfur, 0.05 pounds per bushel. And so this is another one that is becoming more and more deficient. Now, another question we had was, if you've got these little damn seed corn kernels compared to a big corn kernel, how long can that little skinny little kernel provide the nutrients it needs to get that corn plant growing? And so what I did, I come from central Nebraska, and our neighbor used to be part of NC Plus, Nebraska Certified Plus. And so I went to them, and I think it's now, was Monsanto, now it's Bayer. But anyway, I went to them and he gave me 9 hybrids. They did not have the seed treatment on them yet, just raw seeds. Gave me those. We ground them up, analyzed them, and what we wanted to know is how long can these corn plants grow? So in terms of what we found in the seed, once again, these are the kernels. There's about almost 50% more weight in a real kernel of corn than a seed corn kernel. But a lot of that is because of the starch. But down at the bottom now, this is the nutrient content in grams per kernel. And what you might expect if everything was even Steven, we would have the red bars being about 2/3 as much as the blue ones. But in many cases here, what we're finding is the red ones are a bit higher than that, proportionately. It's because of that starch. Seed corn, they don't care about the starch. They don't need that. So I told you we'd come back to this again, and only for the purpose of drawing your attention to this early part of the growing season. When we did this big study with Pioneer where we sampled it every week for 15 weeks or so, we collected data, but we didn't start until V3. We knew when we planted it, we knew when we saw emergence, and we had good data out here in weeks 3, 4, 5. And so we had to extrapolate. This line from V3 back to emergence, that's extrapolated. But probably pretty good. When we analyzed those kernels and put it all together, now this is uptake in pounds per acre, and this is calendar day. So what we find is that the uptake of potassium, the red one, was the fastest, but only very, very closely followed by nitrogen. Down here at the very bottom, we have phosphorus, sulfur, and zinc. Very low. Don't need much of that. So how long can these kernels supply the nutrients? We'll let this thing fill in for a second. But this is the nutrients and the number of days based on those growing conditions that we observed. What I picked out was that potassium here, only a little over 2 days based on what is in the kernel. That's not very long. And here's calcium. I talked to the people at the corn breeders, and what they said, well, don't worry about calcium, because he said there's a lot of calcium in the soil. And in fact, he said, when we used to run germination tests, we would put these kernels in a paper towel, add some moisture, and he said we would have some quicklime in the water. We would put some calcium in the water because we knew it would help it germinate faster. It would germinate a day or two faster with some calcium in the water. But in terms of potassium, that root needs to find some potassium fairly quickly. Okay, another little question we had is how extensive do these roots get into the field, and do they share with their neighbor? Do they fight their neighbor? How close to the center of the row do you need to put this stuff? And so I just put up some numbers out here just to get your attention. Once again, we used tag nitrogen. And this is just an example. Now, I did this to illustrate for you that we have some uniform plant population here. What we did, at the V9 growth stage, this is graduate student work, they had a big long screwdriver. And so they would poke it in the ground at an angle so that the tip of the screwdriver was about 6 inches below each plant. And then they would put on the equivalent of 30 pounds per acre per plant. So you spread that out, it only amounts to a little bit of nitrogen. But that was the rate. The rest of these plants, they all got regular nitrogen. Same amount, same ammonium nitrate solubilized. And then we came back 10 days later at V12, destroyed the plant to see where it was. Where was it in the plant? We also did that at soaking time, came back at R1, see what's their difference. So we'll take a minute here. These are plant positions. So this is the stinker that got the nitrogen, the tag nitrogen. And the other ones are our neighbors. And the size of the bar here is the amount of tag nitrogen that was taken up and where is it at? What we found is that much of it, the light colored part, is in the new leaves. I think that's what you'd expect. There was some of it in the old leaves, and some of it was still hanging around here in the stem. Perhaps as nitrate being ready to be taken up and utilized. But in this case, the plant that was one plant away, it was getting a fair bit of that nitrogen, so its roots were over there taken out. By the time you got 3 plants, well, 2 plants away, almost no effect. Now this is at V12. It says that the adjacent plants, these 2 plants together, got about as much nitrogen as the one that we intended to give it to. Now look what happened at R1. A lot of that nitrogen now went to the plant that we intended it to. And part of that, folks, is because corn plants, up until soaking time, they're always growing more and more roots than are decaying. Roots are always decaying, but the new root growth is faster than the decay, up until soaking. After soaking time, that plant has got another place to put the carbon. It's going to put it in the ear. And so after soaking, the new root growth is slower than the die-off. And so I think that's what's happening here is that later in the season, after soaking, these plants, several plants away, don't have as much invasion characteristic. One last slide here, I think on this. Put this together. Once again, plant position, how much of the nitrogen was taken up. What we find is that was put on early at the 12-leaf stage, it comes over and basically parallels what was happening later in the growing season. But 2 plants away, that's about 15 inches away, it's only getting about 10% of what was put on under that plant. So you might say that give it 15 to 18 inches. Plant roots are going to get out to the center of the row, but don't count on them getting clear over to the next row. If you put the fertilizer in the middle of the row, 30-inch rows, it'll probably get it, but certainly not as convenient and fast as if you use something like a Y drop and got it closer. Okay, another little study, and this is getting close to the end. Yeah. Oops, I go back one. Being an old retired guy, I can do what I want. And I have a small grant with the Fluid Fertilizer Foundation. Some of you your companies may be members of that, but they sponsor little grants here and there. And so my question to them was, are these new hybrids different in terms of their uptake characteristics and the laboratory results we get for adequacy in the plant? Are they right for new hybrids? So I went out at soaking time, cut off a bunch of leaves, and the laboratories were very gracious, and they paid for all these analyses. So I was not real concerned about that. But anyway, I was concerned about magnesium, because magnesium is the only element that is in a plant molecule or a plant cell. It's the only one that's active in there. The rest of them are all enzymes or involved, like phosphorus, in transfer of energy. So this goes back to 2012, and a whole bunch of Pioneer hybrids, and there's one DeKalb in there. But the laboratories say, okay, this is sufficient, this is low, that's low category. So some of those hybrids would be in the low category according to the laboratories. 2013, same kind of deal. And there's differences between these hybrids. 14, same kind of a thing. But look at the yields. They're 300, the low is about 260. So they were still yielding very well. But they had concentrations in the leaf lower than what might be recommended. Don't have time to say much about it, but we went out and put some Epsom salts, magnesium sulfate, on some of these plants early in the season, and we were not able to bring it up. It was not a deficiency. It was just the way that the plants are selected. Pioneer also had some long-term studies in Iowa, Illinois, and Nebraska. They let me into these things. These were 2 hybrids fertilized at 0, 50, 75, 100, and 125% of the recommended nitrogen rate. So I went in, had 3 years of traipsing through their fields, collecting samples. And what I did is I put all this together, and this is for nitrogen concentration. And you'll find that they all pretty much fit the line, but each state is a little bit different, and most of that is because of water. So this is the critical level set by the laboratories. That would be 2.7%. This is the case for the early iron. I'm going to go through these very quickly, but this is iron. And what I wanted to show you is that once we get out here to this critical level for nitrogen, it seems that the nutrient concentration of these other nutrients tended to sort of reach a plateau. I showed you this because we wanted to normalize these things because each site was different, each year was different, so I normalized them back to that individual plant or that treatment. And normalizing data, you've got your choice. What are you going to select as the happy medium, the lowest medium, something else? And so what we did, we ended up with 2.7 for nitrogen. We said, okay, that's a fairly stable number. We're going to normalize everything else to those plants that had 2.7%. That's 100%, that's number one. Oh, what's coming next? Okay, so we wanted to know what's going to happen if we have extra nitrogen in the plant. What's going to happen to these other nutrients? So here's a case of phosphorus. You say, hell, nothing's happening. So the data analyzed all of it below 2.7, looked together. Nothing happens with phosphorus. Have luxury consumption with nitrogen. Potassium, oh, maybe something's starting to happen. Ooh, calcium. Magnesium. Sulfur. One of the things we also learned is that the nitrogen to sulfur ratio in a corn plant needs to be about 12, 13 to 1. If it gets more than that, what you're going to start to run into is reduced photosynthesis. it'll look like you've got a nitrogen deficiency. It screws up the chlorophyll. Zinc, manganese, iron, a lot of them fit this trend. Copper, boron. So the example I wanted to leave you with is to say, let's sort of make an assumption that we've got a group of samples out here. When you have enough nitrogen, you don't have a lot of difference here in terms of, in this case, zinc. But you've got some variability out here. Whenever you've got a reduced amount of nitrogen, you've got reduced zinc. So we calculate here that this calculates this value for all those samples and put that together now and say, how damn well did we do? And what are the values for each one of these nutrients? And this is now the concentration. This is variability. And I went to the Ward laboratories and the A&L labs. George is gone, so he can't complain. But anyway, I put a check mark here. The red check mark is that our data would say you need more than 2.7 to get to high yields. The university and Ward labs and these folks, they use a different number, but the green check marks here are where I came up with a higher value. Now, I'm not saying my method is right, but I'm saying we ought to maybe take a look at it. The other point is, before we ever started this thing, I went to some of these old timers and asked them, where did those numbers come from? Where did these adequacy levels come from? Oh, there was a lot of stammering and stuttering. They said, well, this list has sort of grown over time. We really don't know where they come from. But they're different places, different years, different growing conditions. So we're going to leave it at that. And finally, if you look at this in a different way, in terms of nitrogen, my values would be a little bit higher for potassium. The other ones, I'm a little bit higher. This is the other nutrients. The big one was iron, probably. Don't know if there's a lot in there or not, but nonetheless, maybe another way of thinking about adequacy of nutrients. My time's up. I'm over by 5 minutes. Any questions?